As it turns out, cake cutting can also be seen as a game, and that's why we have been exercising that over here. Particularly fair cake cutting is a challenge so big that there is a mathematical field about just that. And one of the tricks is that the person who cuts first gets last. It's one of the rules that seems to be working quite well. Not always do the pieces have the same size though. So for example, if we talk about distribution of natural gas throughout Europe in a cold winter, then we would say probably each country should have gas supply proportional to the number of people in that country. And so if you imagine this to be a cross-cutting of a pipeline which delivers gas through Europe to different countries eventually, then you can imagine that if you do this cross-cutting at many places of that pipeline network, you would have different fractions. It's actually quite challenging to come up with a totally fair solution, because it has to be fair in so many different places, right? There is a paper that has tried to make a contribution to this, and this is the paper you may want to have a look at if you're interested in these kinds of problems. Otherwise, I'll just go into what I prepared for today. And I will be talking about evolutionary game theory. There are different kinds of game theory. We'll come to this later on. And we'll talk about tragedies of commons, among others, and emergent collective behavior. Right? I'd like to start asking you, what do you know about game theory? So this is a quick overview of what's going to happen, most likely, in this class today. I'll start with the motivation, talk about social cultural evolution, then mention the different kinds of game theory, focus on evolution game theory, and in particular on imitation and coordination games. If there's still time, there are so many other subjects we could cover, like spatial and migratory games, evolution of moral behavior, revolutions, conflicts, and of course, any of those subjects could be chosen by you for your projects and extended upon, right? There are many papers, easy to find, and one of the reasons why so many people are interested in game theory is not only because it's not always simple, you need to think about it, it's sometimes quite surprising, and people like that. And on the other hand, there are some really big problems that haven't been solved yet. And it's about your future. Even though there are 8 billion people on this planet, we haven't really solved those problems yet. Some of those problems are thousands of years old. Still, we haven't solved them. How could that be? How bad is that? Could you make a difference? Environmental pollution, climate change, overfishing. Yes, how to get sustainable on this planet, is really a challenge. And the bad news is if we don't manage to find solutions, it could really totally get out of control, and we'll have to pay the price. It could be quite painful. I don't want to say I totally agree with everything which is in this plot, it has been debated, but at least we need to think about this, talk about it. And in this context, what you often hear is this paradigm of the tragedy of the commons. This is back from the 60s, as far as I remember, or early 70s. And it basically suggests that if everyone separately tries to do the optimal thing, which we often also call selfish, it's not necessarily going to result in a favorable outcome. And if things go wrong, then we call that often the tragedy of the commons. Nobody wants to destroy this planet. Let's suppose so, that's at least what I believe, but still, it could happen as we, pursue our life. And the question is what to do about that. Garrett Hardin, I recommend you to look into that person, has a controversial history. I want to say that really, and I don't fully agree with him at all. But those are established paradigms, which are part also of the narrative when we talk about climate challenges, environmental challenges, and so on. And some people have said that because things can go wrong, if everyone is optimizing by themselves, selfishly so-called, because of that, some people have proposed we need to have centralized solutions and control to avoid that tragedy of the commons to happen. But that would come with a lot of data collection, including perhaps mass surveillance, very controversial, because it's not just about resources, it's also about the use of resources. It would be about control, and that would interfere with freedoms. And so the question is, would we really want to have that? Is it really necessary to come up with a good and sustainable solution? And we're talking now about your future, right? So I think it's really important that we figure out what are the options that we have to solve those challenging problems that we're going to face in the future. So do we need centralized control or not? And in this course, I'm trying to give you a perspective which basically suggests that we can solve our problems not necessarily by centralized control, but by decentralized coordination mechanisms. We need to have the right kind of mechanisms that would make the world work. And what mechanisms would those be? And those mechanisms, by the way, would also allow us for freedoms. But not freedom in the sense that everyone just wants, does what they want, what comes to their mind. That would be anarchy. It would not be coordinated. And obviously, without coordination, things could be quite chaotic, and it could be conflict and war. And I guess most people don't really like that. So game theory allows you to learn quite a lot about those things that we really care about these days, and many people have been caring about always. All right, so I'd like to mention also that people actually are not as selfish according to experimental research, on average at least, as it's often claimed. Many people are altruistic, do care about others, not fully selfish. They don't always optimize, many of them. They rather satisfy, they're happy with a certain level of quality or level of resources. They don't need to have everything. But companies, they typically optimize. So if we talk about tragedies of the commons, perhaps we should talk about, do we have a tragedies of the companies in a market if those companies don't coordinate with each other? Yes, and can we reach coordination in a decentralized way? And this is really something that I find very interesting. And an important point is really that interaction rules can make all the difference, right? So what you see over here is a picture of part of this planet Earth, which in many places is a beautiful planet that we care about, want to preserve. And here it failed, basically no trees. And here it's raining. And the only difference is that there's a border between two countries in between, and apparently there's a different style of organization of how to go about natural resources on both sides of that border. So there are rules that fail, but also the good news is apparently there are rules that work. So what makes the difference? I mentioned already that some of the problems that humanity is faced with are hundreds, if not thousands of years old. And often they're being called social dilemmas. Social dilemmas are situations where it would be favorable if people do one thing, but for some reasons, it's unlikely to happen this way. And as we'll see, it often has to do with instability. That means the desirable solution is not stable. And that's why something else happens. Now, one of those social dilemma games that's well known is called the stick hunt game. And, sorry for that. It's the name that has been given to it. And basically, the point is that many thousand years back, when we didn't have vertical farming yet, people were hunting animals to survive. And they could do it by themselves and perhaps manage to hunt a small animal like a rabbit, or they could hunt a stag, providing food for so many more people. But that required cooperation, right? Now, in these days, we don't have this kind of problem anymore, I guess. We would think, but in a more general way, we still have it. If you think about getting a paper published in a small impact journal versus getting a paper published in a big impact journal, cooperation could make all the difference. In that case, no animal has to die, but we still have the same kind of challenge over here. And by the way, I'd like to encourage you to come up with a veggie version of this game. Perhaps we need a new name for that. All right. Another social dilemma game that is well known is the public goods game. And for everyone who has been living together with other people in the same apartment, probably knows what I'm talking about is, how to organize the cleaning of the apartment, who does the dishes, how do you get that organized? And there's some people who do the work, and here the games are called collaborators. But there are other people who don't do the work, who also benefit from the cleaning of the dishes or the apartment without doing anything. And those are called free riders. And those are typically not very popular. And it's not so easy as one might think to make sure that everyone would be cooperating. And this kind of game is called the public goods game. So some people invest into a public good, and then what results as from that investment basically being shared by everyone. When will we find a cooperative outcome of this? When will we find a non-cooperative outcome? No, these kind of problems are more widespread than you would think, like tax evasion, for example, could be seen as a problem of this kind. In some countries, it's a bigger problem than in other countries. And in that case, typically, you don't have good public infrastructure, and everyone is suffering from that, right? So, how to solve those social dilemma situations? It makes the difference between a better future and a worse future, right? And in fact, over thousands of years, people have come up with different kind of solution approaches. Each of them has advantages and each of them has disadvantages. So there's no one size fits all perfect solution that everyone would like in any kind of circumstances. One of the earliest approaches, and now I'm giving a little bit short cultural history of social mechanisms that have been invented in order to overcome those social dilemmas. One of the oldest mechanisms has been kin selection or genetic favoritism. And basically that advantages have been given to offspring. Even inheritance law today, in a sense, is still in the tradition of that kind of thinking. It's not perfect. You know, you could say it's unfair to everyone else. In fact, it also has created something like clan thinking and conflicts between family clans and these kind of things, and wars even, blood revenge and all these kind of things. So apparently this mechanism is not doing a good job in all circumstances. And so people have been moving on to figure out other kind of mechanisms that would overcome social dilemmas. And one of those mechanisms is peer punishment. So basically, non-cooperative people would be punished by others. And here in Zurich, there's a very famous professor, very close to the Nobel Prize, many people think, Ernst Fehr, has been looking with colleagues into this problem and has made experiments in the lab and has actually shown that punishment can stabilize and even increase cooperation in situations where it would not happen without punishment. Okay, but who wants to be punished, right? I mean, it's not necessarily the kind of society we want to live in. And so let's move on and see what other kinds of mechanisms are there. Again, I'll present them all, probably more than 100 by now. And some work here and some work in other circumstances. And importantly, eventually people became peaceful enough to live together in communities. And living in communities implies repeated interactions. And this is important because in many cases, people would be cooperative to people who have been cooperative to them, and uncooperative to those people who have cheated them and exploited them. And it turns out this mechanism, tit for tat, is one of those rules that actually has this logic inbuilt. If you've heard about it, this can stabilize cooperation. Then eventually what happened is that through this additional level of cooperation that could be established by repeated interaction, it's also called direct reciprocity, by the way, that is comes about by this. So I help you, you help me, that's the logic of it. Eventually, communities became more successful through that cooperation, and people could differentiate So not everyone would have to grow grain or be a shepherd or whatever, and do everything needed to survive. But some people were growing food, and others were shepherds, and others were selling goods at markets, and others were priests, and others were kind of medical experts, and so on, right? So people could do what they were best at eventually. I mean, not always, of course, but that altogether helped society to thrive. And then next thing that somehow happened was that there was trade established between different settlements. And there's, of course, research about that. For example, a particular well-known sociologist has been looking into the Kula ring, and that was basically a barter economy where people have been exchanging goods for each other a long time ago between islands. So they had kind of a cyclical, that's why it's called a ring, system of barter trading. And of course, we don't have that anymore because in the meantime, money has been invented, and that's a kind of indirect reciprocity. So if you have a good, like those streets over here, and want to get something else what you need and you don't have, you need to find not only a person who has the stuff that you want, but you also need to find among those people who have to offer what you want, you have to find a person who would like to have these sweets in exchange. How many would perhaps say, no, I don't want this sweet, I would have liked cake, but you ran out of cake, right? So I won't give you what you want. Things have become a lot more simple through the invention of money as an intermediary value. That's kind of indirect reciprocity. And so, if I want to get the goods that I'm interested in, I would just give money. And the other person who gave me those goods I wanted to have will get what that other person is interested in exchange for the money that the person got. All right. Eventually, then institutions were established, courts. So peer punishment was kind of replaced by a more centralized punishment. Schooling and teaching spread, and now you're here, see, and scientific knowledge was accumulated, and so on and so on. So kind of those are all very important points in human history, I would say. I mean, typically we tell history as, in the year 333, there was this war, and in the year 445 or so, there was this war. I think we should start talking about history in a different way. We should really write up what were the accomplishments that made societies thrive. And finding a new cooperation mechanism is actually really one of those important accomplishments. If you look into a history book, you will rarely find this written out. I think that should change because, if you call people who went to war heroes, then, we would not be surprised there would be further wars. If you want to live in peace, then let's talk about those people who managed to establish peace. And how did they do that? Because that's what we could learn from, right? But now it's time to get a bit more formal, right? We're at Idiaser, so now eventually you knew that would be happening. There would be a mathematical formula coming up. I'll not be too cruel to you. I'll not show too many formulas, but a little bit of essence we need to have. All right. And we want to basically formulate and study models for the evolution of coordination, cooperation, and more. But before we do that, let's formally define what game theory is about. You have learned already from Heinrich that John von Neumann, who had links to ETH, was really one of the key persons. Together with Oscar Morgenstern, they invented game theory. And here is the book. That's already the 60th anniversary edition, and that was already some time ago. So game theory is a mathematical discipline providing a set of analytical tools and solution concepts which have explanatory and predictive power in interactive decision situations when the goals and preferences of the participating players are potentially in conflict. Very long sentence and probably could be made even longer, but it has some of the essence of it. And it's probably not by chance that it happened at this time. You know, a war was still ongoing, as you know. Resources were short. The question is, how could you win? Perhaps not the war. How could you win peace? You know, that's perhaps how we should really think about it. All right, and before I go into evolution game theory, I want to know from you what you would find interesting to learn about game theory. And in fact, there's a concept of bounded rationality in order to account for how real people behave in a better way. As I already indicated, they're not always behaving in a fully selfish way. And that has also implications for predictability based on models, assuming full rationality. I just saw that there is a new special issue published about bounded irrationality. So there's this as well. Now, reinforcement learning is actually a pretty recent concept as compared to when game theory was born. It was not always a subject of great interest, but in recent years, it's becoming really a big field, a very important field. And it turns out that those learning agents, they don't always behave in the way that would be expected according to selfish behavior. So they could overcome some of those social dilemmas. And that is kind of interesting. So recently I've been putting it into a phrase that I called being smarter by less rationality. So rationality is perhaps not the concept that's going to save the world. Perhaps we need new kinds of smartness. And all those learning concepts are interesting in that connection. There are at least 3 different frameworks for game theoretical reasoning. Classical game theory is about Nash equilibria and so on. Evolutionary game theory is more about dynamics. What happens until you get into an equilibrium, if there is one, and there are also other kind of solutions, chaotic, repetitive, and circular, and so on. And there's behavioral game theory, which is more based on experiments and assumes often bounded rationality. And I want to focus on evolutionary game theory, okay? And here's one of the papers that I've written about it, and what I introduce now is explained there in more detail. So I warned you, I will happen, right? So here's the mathematics. So as you can see, what we're interested in is the relative frequencies of strategies or just imagined behaviors I at time t in a subpopulation A. Let's assume the overall population may be made up of different kinds of people. We'll not pay much attention to that later on. The different subpopulations A. And what you want to know is how does that relative frequency of behaviors change in time? And this is what this differential equation is about. It's called the master equation because it somehow masters the process. And what can happen is the following. So people showing behavior I may change their behavior towards some other behavior I prime. That happens with a certain transition rate WA. And of course, any other kind of behavior would reduce the proportion of people showing behavior I. So we sum up over I prime in order to get the overall outflow from behavior. Okay. On the other hand, those people who were showing another behavior I prime at time t, they could change to a behavior I, to the behavior I. Again, with that transition rate WA. And again, we have to sum up over all the other behaviors that could change to I, and that basically defines the inflow into I. And the difference between inflow and outflow defines the change in time. Okay? Yes? This is the relative frequency, or some people would perhaps also say probability. And this is a transition probability. This is the probability of finding behavior I prime at time t. This is the probability of changing behavior from I to I prime. Okay. Now, as you can see, we are already in the second equation. All right. Getting there. So we have to specify the transition rate, and there are different possibilities to do that. But we are looking for a specification that makes sense in the social sciences. And we're talking about interactions of people, right? So people could, for example, spontaneously change their behavior. And there's this phenomenon called trial and error behavior. So sometimes you try something new, and that would be reflected by spontaneous transitions, okay? But in many cases, people are being triggered by other people to change their behavior. And it could be in an imitative way. That means you would change your behavior to adapt the behavior of another person you are interacting with. So that is proportional to the probability of meeting other people with this behavior I prime that you adopt. It could also happen, however, that you don't like the behavior that the other person is showing, and that's why you change your behavior to be different. And that would be called avoidance behavior, okay? So here we have, in other words, assumed three kinds of transitions happening from behavior I to I prime, spontaneous transitions, imitative processes, and avoidance processes. Okay. Now it turns out that imitation is a terribly important mechanism in social systems. People imitate a lot, and they do it because you don't have to learn everything from scratch. You just learn from somebody else who has already learned how to do this or that. It's much faster in many cases, right? It's efficient. And that's why we basically forget about spontaneous transitions and avoidance processes for a moment and focus fully on imitation processes, right? To make your life simpler. I hope you like it. And then the question is, how to specify also this transition probability? And what we'll assume is that people will change their behavior I to I prime only if the expected success of the new behavior will be greater than the expected success of the old behavior in all the interactions with other people. And otherwise, there would be no change of your behavior. And you want to improve. Yeah, let's be honest. And then we only have to specify further on how would expected success be defined. And it's basically given by the payoffs. So if you show behavior I and meet another person showing behavior I prime, what happens then? The outcome, we have a value for you, good or bad, and that would be measured in terms of a payoff, measures your success. Okay? And that payoff happens, the more frequent, the greater is the probability of meeting a person with behavior I prime. So you have a weighted average, basically. It should be I prime here, not I double prime. And that defines the expected success. All right. Now, if we put this into the previous equation, the so-called Boltzmann-like equation, it's called Boltzmann-like equation because if we put this into this, there's basically a quadratic dependence on those probabilities. They're pair interactions, interactions between two people, in other words. And so if we now put the simplified specification for that transition rate into the master equation, then we get just this. Oof, much simpler. And so you're rewarded for that calculation. And this equation is known as replicator equation. It happens to be known from biology as one of the key equations in the theory of evolution, biological evolution. And game theory people have been using this equation, even though we have very different adoption laws in biology. There's inheritance laws, there's genetic stuff going on. And so there's a very different basis. And what my paper basically did was to explain why you can use that equation in sociology or social sciences, because there is another derivation based on imitation that makes sense from a sociological point of view, which also leads to this equation. Now, what that equation says is that basically those behaviors or strategies have an expected success greater than the average expected success, those will spread, and the others that are less successful will eventually fade away. Okay? This is a simple version. It can be extended by trial and error and all sorts of interesting phenomena. I'm not saying this is describing everything. There's a lot of very non-standard things that happen as well, at least as interesting as this. But this is one of the key equations of evolution game theory, and that's why I'm introducing it to you. Okay, and now we want to see it applied to a real life problem. And we'll start with coordination and then move on to cooperation. Okay. And you all know this problem because you're moving around in the city and you meet other people and you need to manage to walk around other people. It's a coordination problem, right? You have two options, go left or right, and the other person as well. And if, yes, if one goes right and the other one goes left, they're still standing in front of each other, have been unsuccessful walking around each other, zero payoff as a result. And in fact, this is what you want to put into the payoff matrix eventually. So one of the findings that I published about in the past is that there is actually the phenomenon of lane formation. So people walking into opposite direction just don't mix as expected, perhaps, but instead there are lanes of uniform walking directions that separate from each other and that make actually walking more efficient. All right, so, and as I show over here, in many countries in Europe, there's a preference for the right-hand side. But this is not the case all over the world. There are other countries where it's just the opposite. And it's equally good in terms of efficiency and whatever you could think of. In Japan, for example, people walk on the left. That's absolutely fine. But then the question is now, why do in some countries people walk on the right and in other countries people walk on the left? How can we understand that? That there are behavioral conventions. How do they come about? It's a coordination game that produces a coordination. The coordination implies a behavioral convention. And this is why I like this game so much, okay? So back to the two person want to walk around each other. And as I said, if both go left, they succeed. So there's a benefit B greater than 0. If both go right, the same happens, they succeed, there's a benefit. But if one goes left and one goes right, then they're still standing in front of each other. Same thing if one goes right and the other one goes left. And so there's a payoff of 0, right? So this is a payoff matrix of a coordination game. You can generalize it a bit, but this is certainly a coordination game. So, and then the question is, what happens if we plug in this payoff matrix into our replicator equation? Let's just look into the equation, right? And there's a paper where I did it for the first time. Okay, now we can calculate the expected payoff, and it's E equals BPI, comma T. We can also calculate the average success of pedestrians, since it's A. It's basically the sum of those two, E1T and E2T. And then we can plug this into the replicator equation, where I've abbreviated the average expected success by A. And see what we get. It's this equation, which I've already written in a form that splits up into different factors. Right, now what do you see from this equation? Are there some mathematicians or physicists in the room? No? Oh, okay. But you can do that too. I mean, basically, what the first thing we do is we want to know what is the stationary solution, the solution that does not change in time. For this, we set this dp dt equals to 0, okay? Then if there's 0 on the left-hand side, what are the solutions of that equation? There are actually 3 stationary solutions, okay? Hey, that's nice. Not always can we actually factorize the replicator equation, right? So it tells us what are the stationary solutions. Effect either p equals 1/2. That means we go 50% to the left and 50% to the right. That sounds like the natural thing to do when the world was created and people were working for the first time, you know. But there are also other solutions. P equals 0 and p equals 1 are stationary solutions. Now, what happens really? Now, the next thing one would do is a stability analysis. So we look at what would happen if we vary a little bit away from one of those stationary solutions. Would that deviation from the stationary solution shrink? Then we call it a stable solution. Because the system stabilizes, goes back to the stationary solution, or would the deviation grow, which means you would go away from the stationary solution into one of the other stationary solutions. And there's a mathematical technique called stability analysis. I really love it. I'm not sure you do, but it's so nice if you can calculate something. Yeah, and anyway, so let's assume we start with p equals 1/2, 50% going to the left, 50% going to the right. It turns out this is an unstable solution. That means if by any chance we have a little deviation from that 50-50 percentage, the people would eventually go into one of those solutions which turn out to be stable. It means either everyone will end up walking on the right or everyone will end up on the left if there's no trial and error behavior, which we have skipped. All right? And that means there will be eventually a behavioral convention. One of those possibilities will win through, and most people will do that. Okay, and then you can change the payoff matrix and put other values in there, and there are different classes of payoff matrices, and one of the prisoner's dilemma, and it's characterized by a situation where cooperation would be rewarded for both players. We'd be good to both cooperate. But it turns out that T is larger than R. We call that temptation. That means defecting, not cooperating, would actually be tempting because it could earn more payoff. While cooperating when the other person defects would be really bad for you. Get a very poor payoff, S. So assume you start both cooperating, but then the other person wants to get more payoff and starts to defect. And then they say, oh, that was not nice. I will never have myself cheated again by that person. So you also change the behavior. You won't cooperate anymore. And you both end up over here, which is a punishment, a very low payoff. You could get both, or you could get this, but you will end up getting this because that solution is unstable. That's also why cooperation and tragedy of the commons erodes. It's the instability of the desirable outcome. Okay. It's tragic, you know, it's mathematics that makes that happen. Yeah. So yeah, in the prisoner's dilemma, detecting is tempting and cooperation is risky. And yes, I'm finishing here. And so depending on the size of those different entries, the payoff matrix, you either have a prisoner's dilemma where cooperation is unstable, defection stable, or you have a harmony game where cooperation is stable and defection is unstable, or you have a stacked game where both cooperation and defection are stable, but the outcome depends on the initial condition. that you could have a sandwich game where cooperation and affection are unstable, but a certain fraction of cooperation is stable.